Hi, I'm Marco Speroni, and I'm excited to share with you the final project my team and I created for our mobile and ubiquitous computing class, the Smart Planter, a smart garden advisor. This is an ESP32 powered device that helps gardeners choose the best plants for their garden by analyzing the specific environmental conditions of each spot. So what exactly is the Smart Planter? It all started with a common problem. Many people, from hobbyists to professionals, don't know the best place to plant different species in their yard. Planting success is highly dependent on matching a plant to its ideal environment. While you can get general advice, gardens often have microclimates, which are small areas where sunlight, temperature, and humidity differ significantly from the rest of the yard, and these can have dramatic effects on the plant's health. Our solution is a smart, portable device that provides data-driven recommendations to solve this exact problem. Here's how it works. The device, which is built around an ESP32 microcontroller, acts as a sensor hub. It collects data on local sunlight, temperature, and humidity. This data is then sent to a cloud database and visualized on a user-friendly dashboard. Based on these real-time data, the system can help generate recommendations for suitable plants, taking the guesswork out of gardening. Our development process began with a thorough research phase. We had to consider several key components to ensure our prototype would be effective. First, we had to find a main board that would support Wi-Fi so the device could send data wirelessly to our database. The ESP32 was the best choice because it enables wireless communication at a very low power cost. Next, we had to choose sensors that were compatible with the ESP32. We selected the CHT31 for temperature and humidity and the TSL2561 for light intensity, as they provide accurate measurement via the I2C communication protocol. Power was a major consideration. For the device to be useful, it needed to be portable and last in the garden. We carefully calculated the battery consumption and designed the system to be very power efficient. Finally, we needed a physical enclosure. We looked into 3D printing for the device case, which would allow us to create a custom design to protect our electronics while still allowing the necessary airflow and sensor exposure. And here you can see the results of that process. On the left is our initial prototype on our breadboard, showing the ESP32 connected to the light and temperature sensors. In the middle and on the right, you can see the final 3D casing we designed. We went through several iterations to get this right, ensuring all of the components, including the battery, fit securely inside. On the bottom, you can see a screenshot of our UI dashboard. This was our web interface, which we built with React, that displays the real-time sensor data from the device. It shows the current temperature, humidity, and light exposure, making it easier for your garden to understand the conditions in a specific spot at a glance. Let's dive a bit deeper into what we built. The final case design successfully houses the ESP32 board, our sensors, and the battery. A key feature of the design is that it provides enough airflow for accurate readings while also giving the light sensors proper sun exposure. To manage battery consumption, we implemented a power-efficient deep sleep protocol. The ESP32 wakes up at set intervals to take readings and send data, but otherwise remains in a low power state. We also minimized Wi-Fi uptime to further extend the battery life, making the device practical for outdoor deployment. Of course, this process wasn't without its challenges both on the hardware and software side. On the hardware front, a major hurdle was refining the enclosure to protect the sensors from the elements without compromising the accuracy of the data. Another challenge was debugging the hardware interactions and ensuring stable Wi-Fi connectivity in an outdoor environment. On the software side, we had to work with communication protocols that were new to us and deal with various drivers to get the sensors and ESP32 to talk to each other correctly. One of the biggest changes we made was to our data transfer pipeline. Our initial idea was for the ESP32 to host its own web page, which would have required the user to manually switch Wi-Fi networks to get the data. This was clunky. After discussing with our mentor, we pivoted to a much better solution where the ESP32 connects directly to the user's home Wi-Fi and automatically reports the data to Firebase. This dramatically improved usability. This project was a fantastic learning experience. Our team gained hands-on experience with ESP32 hardware, developing a React UI, and the importance of client-focused iteration to improve usability. Our main success was building a functional end-to-end system. We created a working MVP that accurately collects environmental data, integrates with Firebase for real-time updates, and displays it on a functional UI. We're especially proud of overcoming the sensor communication hurdles we faced early on. The biggest challenges were related to the hardware environment interface, ensuring real-time syncing was reliable, and designing the MVP data pipelines. Due to the project limited timeline, we were unable to conduct long-term testing to truly validate whether our plant recommendations led to better growth. While we are proud of our prototype, there are many exciting directions we could take this project in the future. We'd like to expand the system to enable real-time plant health alerts, notifying the user if conditions become unfavorable for what they've planted. A dedicated mobile app would make the system even more accessible. We could also explore making the unit self-sustaining by adding a solar panel. Further work would also involve long-term field deployment to track actual plant growth and expanding the plant recommendation engine with more advanced machine learning. Overall, the Smart Garden Advisor successfully demonstrates the feasibility of using localized real-time data to make gardening more accessible and sustainable. Thank you for watching.